So when we look at a function like this, it has a minimum value, okay? When we look at a function like this, it has a maximum value always. So when a is positive, we have a minimum. When a is negative, we have a maximum. That's our general trend that we can remember, okay? Remember that the y-coordinate is called the value of the min or the value of the max. And the x-coordinate is called the location of the min or the location of the max. So on a graph, if we had something on a graph such as this, okay, let's say that was the coordinate. You would say there is a maximum value of 8 located at 2. Well, again, the maximum is at 2 with a value of 8, sure. But you need to emphasize that because, again, the idea is that when we look at these functions, we're really applying them to word problems. So the y value is always the value you're going to get as an answer. The x value is when it occurs. So the maximum occurs at 2, and its value is 8. Is that clear? So in your notes, and I've emphasized this in the video several times, you should have little notes that say location, and this should say value.
When we do our word problems, we have to write those answers.
So it depends on the problem. For example, there's some of your problem set problems that say, determine the values of x and y that give the maximum or the minimum area or the minimum whatever, the sum of the squares one was one of them. Then you would just have to list the x and y. But if it says, find the maximum area attainable, then you actually have to figure out, what is the y value? What is the value of the max area? And you have to make that statement at the end.
And also, do we have hard problem sets?
No, this is the one you're doing by yourself. That's what we said before break. When is it due? When does it due, guys?
So next week.
Thursday. I think this week.
When is your test?
Friday.
Good. Okay. Please don't forget, guys. Again, it's due Thursday. Your test is on Friday. It's due Thursday. Your test is on Friday.
The week after break, they have like 3 tests.
Yeah, I have 4 tests.
Well, this test has always been scheduled for me. You know that. You know what it is?
Every teacher
The quarter.
Every teacher says that.
You don't need to yell. You can raise your hands, guys. The quarter's over.
Oh yeah, it's like in a week.
Yeah. Guys, your original test in this class was actually, I think, on like Wednesday. I pushed it to Friday to give you more time to study, to be honest. Because I felt like we needed a little bit more time. Alright, so what I want to do is take a look at an example of just a function and then apply it to word problems. So let's take a look at one function. So let's say we had the function, let's say j of w equals 3w squared plus 4w minus 7. Okay? And let's say this problem said, determine the maximum value of the function. Determine the max or minimum value of the function. First, we have to take a look and identify which one it is, right? So, Ian, just based on the a value, what kind of a graph do I have here? Is it going to be? Yeah, it's going to open up. So immediately, we don't care where it's on the graph, right? All we know is this. That's what it's going to look like for sure. So, Ian, what could you classify this as? A max or a min? A min. Remember, a min is like the low point. A max is the high point. So this is a min. So for this problem right away, yeah, there's definitely a min. So now what we want to do, though, is determine that minimum value. The value. The minimum value. So what are we looking for? The y-coordinate. But to get the y-coordinate, Kate, what do we need to get first? The x. So really, even though it says find the max value or the min value, you still need to find the x value. Okay, and then you can plug that into the function. What goes through the vertex always? What dashed line? What do we call it? Yeah. So again, it does not matter where this is. Notice I didn't even draw the xy axis. I don't care. Just go ahead and do this now. Just to remind yourself. Okay? So if you could find the axis of symmetry, that's the x-coordinate of the vertex, always. So let's go ahead and do that. What is the definition of the axis of symmetry? In variables, sorry. The definition in variables of the axis symmetry.
H.
H, good, when it's in vertex form.
Oh.
But it's in standard form, right?
Yeah.
So what do we use instead of H? X equals negative,
B over,
negative,
B over is. Forget it.
negative B over,
2AC.
not 2AC, 2A. Negative B over 2A.
Close.
Wait, why can't we
You're
just find
confusing
the
the quadratic
vertex?
formula.
You could find the vertex by completing the square. That's fine. You can do that as well. But that's a little bit more work, isn't it? Right? You'd have to move the 7 over by adding it to the left-hand side. You'd have to divide through by A. This is going to give you a messy fraction. So in this case, Ian, I would choose just using this method. So you can always start by finding the axis of symmetry. So we have negative 4 over 2A. Okay, A is 3. So we get negative 4 over 6, or negative 2/3. That's the x value. So if I were to plot this and write it as a point, this is negative 2/3. But what do I really care about in this problem? The y value. So what should I do with negative 2/3? Yeah, please take that. And by the way, yeah, I wrote x. These should be w, right? Even though they're x's and y's. But that's really the w value.
What do you do if this is a problem? You know, it's like it's in fraction form, how do we graph it?
Yeah, so when it's in fraction form, if you're going to graph it and try and graph the point, I would probably make it a decimal, yeah. Convert it to negative 0.6666, etc. Okay? So let's take negative 2/3 and plug it into the original function. So j of negative 2/3. Now that's going to be messy, isn't it? So on the test, please guys, God bless you, if it's not given in a fraction or if it's not a multiple choice, just plug it in your calculator and see what you get as a number. Okay, you can use your calculator in the test, use it wisely. Say it was a multiple choice and it was in fractions, you needed to do it, let's see what we get. So I take the negative 2/3 and square it, which gives me 4/9. The 4 times the negative 2/3 gives me negative 8/3. So that's at least simplified so far. The 3 and the 9 reduce, right? Everybody see what I'm doing? Cancel, cancel, make that a 1, make that a 3. Okay, so 4/3 minus 8/3 is negative 4/3. Again, this 4/3 minus 8/3, subtract the numerator, 4 minus 8 is negative 4/3, minus 7. And at this point, you'd have to convert the 7 into thirds. How many thirds is 7? 21/3, right? Right, how do we do that? We multiply by 3 over 3. That gives us 21/3. Negative 4/3 minus 21/3 is negative 25/3. Now, as a decimal, that's simply negative 8.3 repeating. So, what is the minimum value? The minimum value is negative 8 1/3. The location that occurs at is negative 2/3. So again, location is what you get from the axis symmetry. When you plug the axis symmetry back in, you get the vertex value, which happens to be a minimum of negative 8 1/3. Okay? So a lot of this comes down to figuring out and remembering how to find the vertex. If it's given in vertex form, it's not difficult at all. Right? Is that clear? It's not difficult when it's in vertex form already. All right. Other stuff for 7-7 was the roots and the sum of the roots and the product of the roots. So here's your general thing to remember. And let me go over an example problem that might be useful for you. The sum of the roots, remember, comes from the middle term, and the product of the roots comes from the last term. So when you have a function like this, Okay? When we went, and I went through the whole derivation in the notes, you don't have to go through that whole derivation and where it comes from again. But remembering that this right here is really like the negative sum of the roots, and this is where the product of the roots really goes. Okay, that's the easiest way to remember these problems and to do them. So for example, let me go through an example of this. Joe, give me a number.
6.
All right. And Ian, give me another number.
2.
2. So let's say the roots are 2 and 6. Okay, the roots of this quadratic are 2 and 6. And the problem says, come up with a quadratic function that has roots of 2 and 6. Okay? Well, what is the sum of the roots here? What would the sum of those roots be? Ian? And the product? Is that agreed? Pretty easy to add numbers and multiply numbers, right? And now we just go ahead and plug it into the formula. So go ahead and plug it into the standard form. AX squared minus 8x plus 12. Now what did I tell you to do when you watched the video? What was the key I said about A? What should you do with A? Jared? Yeah, assume A is 1. Okay, assume A is 1. That would be very useful for you. Now, the reason being is this. If you take a look at this quadratic now and you tried to factor it, what would this quadratic factor into? Okay.
X minus 6, x minus 2.
Yeah, and if you found the roots, what would they become?
6 and 2.
Which is what we had, wasn't it? So by letting A equal 1 here, by leaving A as 1, it makes it a lot easier to check my work first. Okay? Now, notice, if your sum or your product was a fraction though, and you had a fraction here, so say this is like x squared minus 8/9 x plus 12. A lot of the time, you're going to be asked to give the equation with integer coefficients. So what would you do to get rid of a fraction if you had a fraction?
Would you like multiply the c term by whatever makes it a whole number?
Yeah, you multiply by whatever makes the largest denominator disappear. So if you had a denominator of, say, like 9 here, but this denominator was a 3 over here, you would multiply the whole equation by 9 to clear out the denominator. So for example, let's make numbers that are tougher here. Let's say we have 2 roots. All right, so we have 2 roots, and the roots are 3/5 plus 2/5 I and 3/5 minus 2/5 I. So a problem like this. Well, a problem like this is very tough to do by looking at root form. So what you do is use the product and the sum of the roots instead. So if you were to add these roots together, when you add them, what happens? What makes this easy to add these?
The 2 over 5i cancels.
Yeah, the 2 over 5i and the negative 2 over 5i cancel. Okay, because you're going to add them together. So what's 3/5 plus 3/5? 6/5. So that's the sum of the roots. So the sum is always pretty easy to do, okay? Because whenever it's a conjugate, the conjugate portion not cancels off. So the positive 2/5 I and the negative 2/5 I cancel one another. But the product of these might be a little bit trickier, right? The product of them can be a little bit tricky. And the product is only tricky because you have to remember a FOIL. But one part that makes it easy is that the middle terms are going to cancel. Okay, notice that you have conjugates. Whenever you multiply conjugates, the middle terms always cancel. And that's a pattern we've probably picked up on by now a lot of the times. So the middle term is not necessary here. So multiply the first term by the first term. 3/5 times 3/5. What do we get from that? Everybody, come on. Jared? 9/25. How about 2/5 I times negative 2/5 I? What do we get from that? Ian?
Negative 4 over 25 I squared.
Yeah. And what's I squared, Kate?
Negative 1.
Negative 1. So So this becomes 9/25 plus 4/25, right? Because again, replace this with a -1. That's a key to remember there. And 9 and 4 gives us 13, right? So the product is 13/25. Well, this makes this useful because now we can plug those into the equation that we started with. So let's go ahead and do that. Thank you. Plug them in for B and C, please. Plug them in for B and C, please. Remember, though, B gets the negative of the sum of the roots. So it's -6/5, right? There. Right? That's what we have here? Right focus. We have this equation here now. So what we see is that, yeah, this is the sum of the roots, 6/5. Remember, it's the negative sum of the roots. This is the product of the roots here, 13/25. But the issue is that we have this denominator now. So, Joe, what can I do for this problem to make this look better, to get all integer coefficients? By?
25.
Yeah. So f of x is simply 25x squared. Now this is going to get a little bit messy. This is going to be minus 30x, and I'll show you where that comes from. Plus 13. So again, what are we doing? We're multiplying this entire thing by 25. Okay, so the first term, is that clear where that comes from right there? The 25 in the front? But then here, when you multiply the 25, you're going to have 25 over 5, really. Which is just 5, and then 5 times 6 is 30. And you can check that. 25 times 6 is 150, and 150 over 5 is still 30, either way. And then the 25 multiplied here cancels with this 25, leaving behind a 13. So a problem like this would have this form. Notice A is no longer 1. So there are times when you're going to get answers that have fractional coefficient values here. These constant terms are fractions. Multiply by the largest of them to clear out the rest of them. Okay? Now, one other way that we solve these problems that would be a little bit useless here. One sec, right?
You're saying, couldn't you solve the problem in fractions?
Couldn't you what?
Couldn't you just take the problem in fractions and set it from there?
What do you mean?
Like, take the -6 over 5 and make that b over, like, can you solve it with the fractions?
You can, but the issue is this that people are having. Like, remember it was C over A and negative B over A? Well, is A 5 or is A 25 now? You see how confusing that could get? If you call this negative B over A, and you call this C over A, then some students have trouble knowing which is A. Well, A is 25 for sure. It's going to be the larger because this really, -6 over 5, you need to write this as negative 30 over 25. And that's where the 30 comes from there. And then it leaves this denominator A to be 25. It's just easier to assume A is 1, get your fractions like this, and then multiply through. And now you can see that A is actually 25. So this is A here. This is definitely C. So there's C, there's A. Well, you don't see B here because you have to make this 25 by multiplying by 5 over 5. That's what gives you the 30 for B. Okay? So it's difficult sometimes to do that, but it depends whichever way. This, I think, is just a lot easier. Now, the other way that I showed you guys to solve these kinds of problems, if you're given simple roots and you're given another point, is to plug it into root form. But the issue is this. Here's root form. Root form looks like the following. Okay, and I went over this in the notes. But the problem is that, what were the roots of this problem? What were the roots of this problem? Chris?
Is it 3 over 5 plus 2 over 5i, and then 3 over 5 minus 2 over 5i?
Yeah, both of the roots were complex conjugates, weren't they? 3/5 plus 2/5 i. Are you going to want to plug that all in right here for R1? If the roots were, say, remember the last problem, Joe, you gave, I think, 2, and then Ian picked, I think, 6. The roots were 2 and 6, right? So you can plug a 2 in there, plug a 6 in there, and it's easy to figure out what the function looks like. That's simple. But when you have roots that are conjugates, complex or binomial, like so if it's like 4 plus root 3, 4 minus root 3, or 7 minus I and 7 plus I, it's difficult to plug those in there. So when those problems occur, it is very important that you use the sum and the product of roots. Again, when your roots, and you should maybe write this down as a little note, when your roots are complex or binomial conjugates, you're better off using the sum and the product of roots. When your roots are binomial or complex conjugates, you're better off using the sum and product of roots. Let's do an example where the roots are whole numbers, and you're given a point, and you have to find the function. Okay, so let's take a look. Let's say the x-intercepts occur at 2 and 7. And f of x contains, let's see, the point 411. Okay? So this is what we're given. We have the x-intercepts that occur at 2 and 7, and f of x contains the following point. Now, tell me, what are some ways you can think about solving this problem? Because there are many ways to solve this problem. I can think of 3 off the top of my head. Completely different ways. All would give you the same answer, but one would be easier than the other, etc., etc. Ian, give me one way.
Plug in the 4 and 11 into the y minus k.
All right. In for the vertex, you say?
I think it's like y minus k equals to like
Quantity a times quantity x minus a squared. That's if you have the vertex. H and k are the vertex. So if 411 was the vertex, you could do that for sure. But 4 and 11 is not said to be the vertex, so we can't assume that. Okay? Good idea, though. Keep that in mind. We'll do that when we do vertex. Chris?
Could you use the function that we used before, f of x equals x squared plus bx plus c?
Okay, you could do that. You could plug it in here. And you would have to use a matrix to solve that. You could definitely do that, though. That's one way to do it. And that works, Chris. That's what I'm saying. There's 3 ways. And this is root 1. So if you plugged into here, it would look like the following. Remember, what are these? These are really points, right? Remember that? Those are really points? So you could plug in all 3 of these points and get a system of equations that would look like this.
Can you do substitution elimination?
Whoops. I mixed them up. Hold on one sec, guys. Yeah, you would have to use substitution elimination to do it. Exactly. Sorry. That would be the first point. Then you plug in the second point. And then the third point would look like this, right?
Why would f of x be 0?
Look at the y value. Isn't f of x y?
Oh, yeah.
Did you see the y values of those points, Joe? Okay, that's what it would look like. We'd have 3 equations, 3 unknowns, and we'd have to solve using a matrix. That's one way to do this for sure. Second way to do this problem. Second way. Jared.
Use the root form.
Root form? Agreed. What would that look like if I plugged in?
Well, first you have f of x equals a, parentheses x minus 2, and x minus 7.
Yeah, so you start by plugging in the roots. And then what would be the goal? We'd have to find still what?
You have to find
Yeah, exactly. So then you'd have to plug the 411 in. So it would look like this. Okay? So for this kind of a problem here, what we're noticing is that method A works, and you can plug it right in your calculator and do it that way. And that'll give you A, B, and C, and it'll be a standard form. That's fine. Method B also works, and you can just go ahead and plug this in and just do it in your head, right? It's going to be 2, be negative 3, it's negative 6. So A is going to be 11 over negative 6. Now, remember for method 2, that it's going to look like the following. We're going to get 11 equals A, and this is going to be, again, 2. This is going to be negative 3. So that's going to be negative 6. So A equals 11 over 6 with a negative. That's the A value. So in the end of this problem, excuse me, what we'd end up getting here is the following. Okay? And now, this kind of a problem, you can't go any further. You can multiply it out and put it in standard form, that's fine. But there's nothing else to do. You don't clear out your denominator anymore. Remember that other problem earlier, where we found the product of the roots and the sum of the roots, and we then clear out the denominator and stuff? That's fine, because we were looking for any function. But now we have a function given these two roots and another point. You know the 411 that we used to plug in here? That 4 and 11 is what allows us to find the A value. Earlier, we were just given the two roots, so we didn't know what A was. Remember we said assume A is 1? When you were given the two roots, you found the sum of the roots, you found the product of the roots, we assumed A was 1, and then we cleared out our denominator by multiplying through. That's because we didn't know what A was, and we really still didn't. We didn't have a third point. But here, we've got the roots 2 and 7, and we've got a third point, which is 4, 11. Based on that third point, when we plug it in right here, that allows us to solve for A. So this is A. A is not going to change. Okay? So if you were to actually go through this and put it in standard form, here's what it would look like in standard form. In standard form, this would become the following. Right? You multiply out the two binomials, FOIL them out, and then distribute the negative 11/6, which is going to be messy. It's a negative, hold on. Okay. Say again? Yeah. I hear that too, it's a video. So take a look. For this problem, our answer for f of x in standard form at the bottom is very, very messy. Everybody see that? Now, it is extremely tempting to say, well, multiply by 6, right? Multiply by 6 to get rid of the 6's. But the problem here with this kind of a problem is that we were given the point 411. If you multiply by 6, it's going to change the height of the function. It's going to make the function wider or narrower. So instead of the function looking like this, okay, negative, going through the point 411 right here, if you multiply everything by 6, it's going to change the height of the function. So it'll have the same x-intercept still. The x-intercepts will be the same, but it'll just stretch it a lot. And that's when you multiply everything by a certain constant, it stretches the function. So it'll still have the same x-intercepts, which were 2 and 7, but it will no longer go through the point 411. So when you're given a third point, so if you're ever just given the two x-intercepts, you can use the sum and the product of the roots and then multiply through by clearing the denominator. But if you're ever given the x-intercepts and a third point, then you want to make sure that you solve, make sure that you solve for the A value by using the third point, not by multiplying through. Okay, there are two different methods. One works, one doesn't. Chris, if you remember the method you started with the matrix we got there, if you had solved that matrix for A, B, and C on your calculator, A would have been negative 11/6, B would have been 99/6, C would have been negative 154.6. And you can check the calculator. It'll reduce them, but it would be with fractions. Same answer. All break, right? Not sick. And then Saturday I started getting like a cold, like really bad. And of course it got worse and worse. This always happens this way. Where did I put my pen now? My pocket. Okay. Let's take a look at some word problems. Okay? Let's take a look at some word problems, see how they're involved. All right, so let's say we've got first or one with like numbers first? Numbers first? Numbers first? Okay. I like the ones with geometry and like the applications.
The numbers.
All right, let's start with the numbers one. Let's say we have the difference of two numbers is 6.
Well, it should be a 1.
3 and 2.
1.
Always use those three.
As long as it's not like 5/3 or like.
Actually, we should say the sum. Let's use the word sum, not difference.
1. Some of the numbers is 1. No, it's 2.
You made me
No,
write
and
it.
no decimals. Some of the numbers is 2 and there's no decimals.
The sum of two numbers is 67.
2 and no decimals. 2, no decimals, no fractions.
Determine the values of those two numbers so that
Mr. Hall's happy.
the sum
Oh no, this is gonna be made up, so it's gonna be really hard.
of the sum of their cubes is a
Parabola.
minimum.
What?
Determine the values of those two numbers such that the sum of their cubes is a minimum.
You get your information.
That's it.
This is
Got the
crazy,
numbers.
Mr. Howard.
Okay?
Got the directions.
So Ian, read it for us. The first sentence, Ian, go ahead.
Sum of two numbers is 67. So 67.
67.
Okay. Julia, read us the second sentence.
I do not know.
Okay. Sorry. Chris, you got the whole second sentence? Okay.
This is the cubes.
Determine the values of those two numbers such that the sum of their cubes is a minimum.
So that's what I know.
Wait, if you split less than 0, could you?
There's no inequality here because it doesn't say anything about that.
That's a minimum.
It is a minimum, but that just tells us that the A value of the parabola is going to be negative, or is going to be positive, so that the graph opens upward.
Oh.
Okay? So here, what is this capital S? What does that mean? Why did I write capital S?
Simple.
Yeah, I heard the word sum. Not simple, but sum. Okay? So what I'm writing here is this, and this is what was tough, and this is what I tried to explain to you guys. The top part is what's called a constraint. Write that down, please. Constraint. Okay? Why is it a constraint? What does a constraint mean? Something that does what? If you put a collar on your dog and a leash, what is it doing?
Keep it going everywhere.
Yeah, it's containing it or limiting its movement, right? Does it limit the dog's movement? A leash?
Yeah.
Okay.
That's cool.
So a constraint is some sort of limiting thing. So what does this mean? It means that the sum of these two must be 67. It cannot be bigger than 67, and it cannot be less than 67. It must be 67. So you are constraining the x and y values to some quantities. For example, Ian, if x is 1, what's y?
66.
So Ian, for every x, you can tell me what the y is, right?
Sure.
If x is 2, what's y?
65.
Yeah, and so forth and so on. So there's a constraint. Is that clear so far? So this is limiting the possible values of x and y. Second, this function we're going to call the objective function. Why it's called the objective function? Because it needs to be either minimized or maximized based on the problem. There's an objective in this problem. What is the objective for this problem? To find the, not to find the sum. That create the what?
That creates the sum of
To be what?
the
Minimum. So the objective, sit back, Ryan, is to minimize the second function. That's the objective right now. We want to minimize this function. It said, find x and y such that the second function is minimized. Okay, is minimized. So we want to minimize this function. Now, remember from graphing, how did you find the minimum or the maximum? You found the what first? With a parabola, if it was in standard form. Not the y-intercept. How did you find the max and the minimum value?
Axis of symmetry.
Yeah, you found the axis of symmetry first, right? Axis of symmetry. But to find the axis of symmetry, we need an equation that says, like, f of x equals everything in x. Or j of w we did earlier equaled everything with w's. But here we have x's and y's.
So would you take the cube root of it and cube the sum? No.
Can't take the cube root simply because, well, there's several reasons why, actually. A cube root here would not get rid of these cubes. Remember, they don't cancel. A cube root doesn't cancel because it's a sum. If it was a product, it'd be a little different. So what we need to think about is this. We need to write this second function only in one of the variables, not in both. So we have to solve for one of the variables in the first function. Solve for y in the first function.
Y equals 67 minus x.
Does everybody agree with that? Does that make sense? Right? And we can take that and plug it in for y. Now, one thing I'm thinking about right now, this is going to become cubic. I did cubes because one of the examples in your book is squares on your problem set, but you should really make these squares. Make them squares or else it's going to make the problem almost impossible to solve. Not impossible, but for what you know right now, it would be. I tried to just make it a little tougher, but that's going to make it impossible right now. Okay? Because your book gives you a problem like this where it says minimize the sum of the squares. So there's going to be one very similar to this in your problem set. Now, go ahead and plug that in for y. So we have x squared plus 67 minus x squared equals s. So again, we're taking this quantity, we're plugging it in for y. Everybody see what we're doing here? Joe, why are we doing this? What's the reason? What has this done for us? Has it accomplished anything? Yeah, by using what though? How are we going to find x? We want to find the, what did Ian say a minute ago we need to find? Before we can find the minimum or maximum value, what do we have to find? Yeah, the axis. So let's go ahead and FOIL this out and collect terms. Now, somebody quickly tell me, Ryan, what do you get from 67 times 67 on your calculator? Okay, so if we FOIL this out, we get 4489 minus 134x, which is the middle term, 67x and 67x, plus positive x squared. Okay, negative x times negative x is positive x squared. So again, we're FOILing that. Now combine like terms and put it in standard form. We have 2x squareds. We have a negative 134x. And we have a positive 4489. So what do we have here now? What we've accomplished is we've got an equation that's in standard form. And what do you notice? The only variable is now x. So we can write this as s of x. And we could have done that up here. As soon as we plugged in for y, we could continue to write all these as s of x, because this is now a sum function of x, only of x. Find the axis of symmetry, we'll continue tomorrow. Find the axis of symmetry, plug that back into the function to find the minimum or maximum value. We'll pick up with these word problems more tomorrow. So if you remember what we had said, I'm going to pause. At this point in time, when you have your actual equation written out, all in terms of x, we say it's a function of x, which is why it's s of x. And now we want to minimize the function. Minimize the function. So on a parabola, the minimum value is always on the vertex, or the maximum value is always on the vertex. So we need to really find the vertex of this equation. How would I go about finding the vertex of an equation? Who remembers from yesterday we talked about this? How do you find the vertex? First step. Good. So we need to find the axis of symmetry first. All right? So negative b over 2a is going to be negative 134, which is positive 134, all over 2a. Okay, so it's going to be 134 divided by 4, which should be what? 4 times 30 is 120. 33.5. Somebody check that, please. It should be 33.5. So this gives us the location of the axis of symmetry. So this tells us that the variable x is 33.5. Before we even go on to find the minimum value, which we'll do in a second, if x is 33.5, we can find y also. Go back up to the top. Yeah, and what do you notice? What's y also? What does y also turn out to be? Yeah. So for any of these problems, a little trick to know. Whenever you're minimizing the sum of squares, and you have some sort of a sum already, they're each just going to be half of that. And you'll see that on your problem set when you finish it tonight. That there's a problem where it says the sum of two numbers is 20. Minimize the sum of their squares. Each number is just going to be 10. But I want you to go through the work and show it. But you'll realize that this is actually not like a coincidence. It's always going to work out that way. The reason being is because if you start increasing one of these numbers beyond 33, well, start with an easy example. Imagine this was a 20, like in your problem set's going to be. So imagine up here, this was a 20. So that would make this 10 and this 10. 10 squared and 10 squared is going to give me what? 100 plus 100? 200. Try any numbers besides 10 and 10. Try 11 and 9. What's 11 squared? 121. What's 9 squared? 81. 121 and 81 is 202. See how it's getting bigger already? Try 15 and 5. 15 squared is 225. 5 squared is 25. That's 250. It's getting bigger again. So you're always going to get the minimum value for the sum of squares when x and y are just the same quantity, or half of whatever this number is. Okay, it'll always work that way. That's just a little thing to pick up on.
The farthest away from each other, the bigger they are.
The larger this number is, the bigger they are, yes. But the further away they are from each other, the bigger the sum of their squares is. Correct. Exactly right. So the bigger the deviation between x and y, the larger the sum of the squares will be. And we want to minimize that, so we don't want any deviation between x and y, so we can just set them equal right away. Okay? Kate?
I'm really lost. You just said that it can be a 20, then how are squares?
And I said,
going to
hypothetically.
100?
Hypothetically, say the sum was 20.
Then why do you want it to equal 200 on the next thing?
You want to minimize the next thing. So I was giving examples. So for example, if this were 20 at the top, to make it easier numbers to do on our head, and you made x and y 10 each, right? And then you plug those in here, you would get 200, right? But then because it's 100 plus 100 giving 200. But imagine now, instead of 10 and 10, they were 15 and 5. 15 squared is 225. 5 squared is 25. That'll add up to 250 here, which is already getting larger. But we want to minimize it, so we want the smallest possibility. It turns out that the smallest possibility for the sum of squares will always occur when x and y are equivalent to one another. And they happen to be half of the sum. Okay? So that's why this answer at the end here, notice we got 33.5. That's half of 67. Okay? So if we want to find out what the value is of the sum of the squares, we could plug 33.5 into the back to the original equation that we had, where we had x squared plus y squared, and just square them both. Or we could take 33.5 and plug it into the actual function. So we can say this.
Couldn't you put in x plus y equals 67?
That'll give you x and y, but that won't give you the sum of the squares. You would have to plug it into x squared plus y squared to get the value of the sum. Remember, you're not only finding the x and y value, you're also finding the sum itself. So you can, if you found x and then you found y, you can go ahead and plug it in for x squared, for y squared, and add them together. Or you can just evaluate the sum function right here, and you'll get the same exact answer. Okay, so if you plug in a 33.5, somebody check this on their calculator, please. See what you get for an answer. Jerry.
You're saying x squared plus y squared is it because we're dealing with quadratics, or?
Well, because the problem, remember yesterday we had said that we want to minimize the sum of the squares of those numbers. That's where x squared plus y squared came from. Okay? It had to do with the actual statement, the problem itself. And somebody else, while I see Chris is checking and Kate, somebody else check this, please. Do 33.5 squared times 2. You'll get the same exact answer. You should get the same exact answer. Kate, what do you get for your number?
I got 2,244.5.
Exactly? Chris, did you get the same?
Oh, forget, I disagree.
Okay.
I multiplied by 2.
That's all right. Can somebody check now, if you plug in 33.5 and square it, and then add the same number, if you do x squared plus y squared, go back into the original. So instead of plugging it in here, let's plug in 33.5, square it, 33.5, square it, and add them together.
We know the same numbers for x and y, so we're just plugging into.
Yeah, that's right.
Yeah, you're going to know that for your problem set. That's what I was saying. But just show the work. Show that if you solve for x in terms of y and plug it in, use the axis symmetry. This happens to be the answer for this specific case. When you're looking at the sum of squares and the sum of them happens to be a number. Always going to work out for this specific case. What do you get, Kate?
What?
What did you get did you plug that one in?
Yeah.
That's it.
It still
Same
gives
thing?
the same
Good,
answer.
okay. So this is the value that is the smallest possible value, the minimum value of the function, okay, of the function x squared plus y squared when x plus y is 67. Now, say again? So this is the location of the vertex. The vertex would be at 33.5, comma, 2,244.5. That would be the vertex. This is the x. Remember, this is the x value of the vertex. This is the, s of x, the y on the graph, but don't consider it y as in what we looked at the equation before. Okay? Let's take a look at geometry, an example of geometry. Let's say we have, I don't know, what kind of a shape do we want to make in this case?
Square.
A square? Well, a square is no work to do.
Hexagon.
How about a square with a triangle on the end of it?
Or an octagon.
That sounds good, right?
Octagon.
An octagon?
A pentagon.
Do you really want to count it up?
Let's say we have the side of a house
What is
with a patio off the back of a house. I'm such a good artist, I know. The patio off the back of the house. And then we have
That is not me.
a triangle, okay, like a pencil, okay, off the back of the patio. And we know that this is an equilateral triangle. Okay, the triangle is equilateral. And we want to
Find the area.
find the dimensions of this shape given that there is 50 feet of fencing, there's 50 feet of fencing to go around wherever you see, okay? And we want to maximize the area of the patio. We want to get the most out of our bang for the buck, right? Get your bang for your buck. Have you heard that before?
We're paying for fencing.
So you're paying for the fencing, so you only can afford 50 feet of fencing, but you want to get the biggest patio possible. So you want to maximize the area of that patio.
You have the money to get a patio. You don't have the money for more.
You just ran out of money, okay? Yeah, you ran out of money and that's all you got is 50 feet of fencing. Just go along with it.
That's
Yeah.
Is that square a wall?
Fencing on the black market, so you buy it legally, that's what you buy.
So you've got fencing, 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 fencing. This is the house. Okay, again, guys, this is your house. It's like the side of the house. The house is obviously is a bird's eye view. We're looking down on the house. Here's the rest of the house. Here's the front door of your house. Okay, you're looking down on the house. It's a huge patio.
What type of engineer?
Enough. So, let's go ahead and give our let statements here. Let's make some definitions and let statements. What have we got for let statements?
I just have a question.
Yeah.
Wouldn't it maximize the area more if you took away the side between the fencing?
Yeah, but you need that fence there. You need that fence there. It's going to make it tougher of a problem. Okay? Yeah. I agree with you, Jared.
Why would you cut the?
Okay, you need a piece of fence there. Make believe it's a patio and then it's a triangular garden attached to the patio. Whatever. Just use your imagination. So, for this kind of a problem here, okay, for this kind of a problem, we have to start with our let statements. What do we got? Give me let statements for something like
I
this.
got it.
Ryan?
Let 4s, no, 2s, two sides, like the area of the square plus the area of the triangle. Equals 50. Or no,
Okay, no.
that makes no sense.
50 is a linear dimension, right? Feet, it's not feet squared. So 50 is the sum of all of the perimeters that we have here. Jared?
Is that triangle equilateral?
Equilateral, yes.
So,
That's what the statement was in the beginning.
did you put a fence next to the house? No.
No, that's why I said it's adjacent to the house. That's what that's showing those lines there. Again,
I'm making
you don't need a fence right here, guys. There's no fence here.
That's the problem.
Yeah, give me dimensions.
Dimensions.
Give me let statements for dimensions.
Let one side equal x.
Which side?
They're all equal.
No, they're not. That's a rectangle.
It was a
Split
square.
it.
You said it was a square with a triangle.
Oh!
You did say it was a square with a triangle.
It's a rectangle.
Okay, let the parallel sides be,
Okay.
be x, and let the three equal sides of the
Good.
triangle be y.
Thank you.
And then you do 2x plus 3y equals 50.
Good. So that's our statement to start. We have two sides of the rectangle as 2x. We have a side of the rectangle as y. And then two sides of the triangle as y as well. So we know that that's going to be 50. So far, so good? Okay. And we want to maximize the area. Okay, we want to maximize the area. What would the area of a equilateral triangle be? Anybody know this one?
Half base height?
It's half base height, but what's the height in this case, Joe?
Y?
X.
The base is y. The height is not x. The height is whatever this is right here. Right?
Also,
Remember Pythagorean theorem? You can use Pythagorean theorem to figure out what it
Y
is.
squared plus B squared.
No, y squared plus y squared equals.
Y squared plus Y squared equals Y.
Turn your head this way, please. You'll see a squared is here, right? That's b squared, and this equals c squared. You have this dimension, you have this dimension. You need to figure out what this dimension is, so you can use.
What is it? What dimension?
You need to raise your hands. Jared, go ahead.
1/2 y squared plus b squared equals y squared.
Well done, Jared. So what Jared is doing is he's labeling this portion right here as 1/2 of y, which is correct. That's half of y.
So that's half.
So he's saying if you want to find out what the height is, this is again trying to find the height of the triangle first. If you want to find the height, it would be 1/2 of y, which is a squared, plus the height squared equals the hypotenuse, which is y squared. Okay, so again, take a look. This is a squared, b squared, c squared. There's a, there's b, there's c. So if you want to find the height, which you're going to need to do this problem, okay, that's the method I would choose to use. So you would get 1/4 y squared over here, yielding h squared, 1/4 y squared, and y squared. Subtract 1/4 y squared from both sides. You're going to get h squared equals 3/4 y squared. Okay, again, subtracting over 1/4. 1 minus 1/4 is 3/4. Square rooting both sides. The height of this triangle turns out to be √3/2y. Okay, that's the dimension for the height of the triangle. Again, the square root of 3/4, the square root of 3, you just leave it. The square root of 4 becomes a 2. The square root of y squared becomes a y. So this would be the height in this kind of a problem. I'd probably give you the height on the diagram. Okay? I'd probably give you the height, but just in case you're wondering how to figure it out, that's how you would go about doing it. So we know the height of the triangle. Okay? And we want to maximize the area of the entire thing. So let's think about this. We've got a rectangle and we've got a triangle. So the area is going to have several parts to it, right? Let's write our area function. What's the area of the rectangle? Which was?
67.
What's the area in variables of the triangle, of the rectangle, What's the area? Come on, people. What is it?
Length times width.
Yeah, length times width, which in this case is x times y. That's the area of the rectangle in this part. Look at your diagram. I'm not going to scroll back up. You should be writing this down. So that's the area of the rectangle. The area of the triangle is 1/2, remember, base. The base of the triangle was y times the height of the triangle, which is over here on the right. So this is the area function in this problem, which is, pretty complex when you look at it right away, but it's not going to be that bad, actually. What we do need to think about is this, though. I have an area function in terms of x and y. You see that? Remember last problem we had x and y and we couldn't do that to maximize or minimize the last one? So go back to your constraint up at the top here. Take a look at your constraint. There's your constraint right there. Think about it. Solve for x or solve for y in this constraint. It doesn't matter which one you want to do. Okay, it makes no difference. Solve for either one of them. Which one do you want to solve for? X or y? Y. How come?
Oh, I was just guessing. Either one.
Either one is fine, but one is better than the other. How come you're choosing x?
That's y times 3y.
Yeah, exactly. Take a look at the area function. If you solve for y at the top, you'd have to plug it in 3 locations, right? As opposed to if you solve for x up top, you can just plug it in right here. Okay, you can just plug it in once, right there. So let's solve for x in the top one. Solving for x, we're going to get 50 minus 3y all over 2. Agreed? Okay, solve for x. Move the 3y over, and then divide by 2. Take that quantity and plug it in right here. And then you'll have an area function in terms of all y. Okay, in terms of all y, and then we can maximize. So let's go ahead and do that. 50 minus 3y over 2.
Why'd you write a? Isn't it just 50? There you
It's the area function. Now, on this right side, what should I do to make this problem a little bit easier? I should multiply, right? So 1/2 times root 3 over 2 is root 3 over 4. Y times y is y squared. So far, so good? Again, I've multiplied these two quantities. 1/2 times root 3 over 2 is root 3 over 4. Y times y is y squared. On this part, what should I do? Yeah, I should distribute. Okay? So let's go ahead and do that now. Now, notice I left a little space next to the area here. It's a function of y, isn't it? So we can write like that now. Remember how we do f of x or g of x? This is a of y. Now remember, x and y, you always think about as your x is your horizontal axis, y is your vertical axis. But in this problem now, it's not a of x, it's a of y. So if you were to graph this, believe it or not, y would go along the horizontal axis. Okay, because this is not a of x, this is a of y. And remember, whatever the independent variable is inside of here, the argument, is the horizontal axis. So the vertical axis would be the area. The horizontal axis for this function would be the coordinate y, or the dimension y, in your diagram. Remember, if you want to label your diagram with A and B, or L and W for length and width, it might be useful. Because some students get tricked up with here when you have the y. They think, oh, that's the y-axis. But the y in this problem is the horizontal axis, because it's the independent variable. So distribute, please. Distribute the y to both of those. You're going to get 50y over 2 minus 3y squared over 2 plus root 3 over 4 y squared. right? Simplify. And notice I'm doing all these steps. It does help. It'll help us a lot when we're finding our answer. 50 over 2 is 25, clearly. Now, the next part, what I would do at this point is come up with a decimal representation. Okay? Might be a little bit useful here, because if you have radical 3 and you're going to be adding it to the other part, it might be tough. So you've got this negative 3/2 y squared. That's really negative 1.5 y squared. What do you get with root 3 over 2? It should be like 1.73 or 72, something like that. Root 3 over 4. Root 3 over 4. Or no, half of that. 0.866 over 2. 0.43? I think it's 0.43, okay. Oops. 0.43, not 4.3. So now what this does is it enables us to combine like terms. Okay, we've got y squared twice. So our area function in the end, if we take negative 1.5 and add positive 0.43, we're going to get negative 1.07 y squared plus 25y. And what this has done for us is we have a function now, a of y, in standard form. This is ay squared plus by plus c. There's no c value. C is 0 in this problem. So what do we do here? If we want to find the maximum for this function, what do we have to find before we can ever find the maximum? Ian helped us out with it earlier. Kate?
The axis is symmetry.
Yeah, the axis of symmetry. Remember, what does this graph look like? Joe, when you see a negative a value, what does that tell you? Which way is the graph going to open?
Concave.
Yeah, concave which way? Down or up? Is it going to look like a hill or is it going to look like a valley? You don't remember? Okay, when a is negative, negative means it opens down. So you're going to have a graph like this. The other way you can verify that is, aren't we maximizing the function? We're trying to find the maximum area. And this is the area function. So the maximum exists at the very peak, at the vertex. If this function had a positive in the front, it would look like this, right? And that would give us a minimum. But we're not trying to minimize the area, so it wouldn't make sense. So whenever you're doing a problem, if it says to maximize the area, you better get a negative a value here to show that the graph is going to look concave down. Okay, and again, what are we trying to find? We're trying to find the value here. So we're trying to find the coordinate and really the y-coordinate. But to get the y-coordinate, we need to get the x-coordinate, which, as Kate said, is really the axis of symmetry. So we're going to find the axis of symmetry by using negative b over 2a. Let's go ahead and do that. Now, remember the axis of symmetry is x equals negative b over 2a? But in this problem, it's not a function of x. What is it a function of? It's a function of y. Okay, so you would really want to write y equals negative b over 2a. And notice, it's just really whatever the variable is in the equation. That's all it is. So negative b over 2a would be negative 25 over 2 times negative 1.07. What do you get for this? Somebody check on their calculator, please. It's a negative over negative, so clearly it's going to be a positive answer. Make sure you put parentheses around your denominator when you type this in your calculator. Hoping around 10-ish. Around 10-ish?
I got 13.375.
13 point...
375.
Agreed? All you're doing is negative 25 divided by, parentheses, 2 times negative 1.07, close parentheses, enter.
Yeah, I got 11.6.
Yeah.
Oh, I didn't put
Okay.
the parentheses around too.
Yeah, there you go. So it's 11 point what?
6.
Joe, what'd you get?
I wasn't doing
Can you check for me, please? Okay, so that'll give us the y value, okay, which is one of the dimensions in the problem. Go back to your original diagram. Look at your original diagram. You had parameters or your dimensions of x and y in this problem. So that's the y value of the dimension. So those are the dimensions of the triangle, really. Okay?
Oh, yeah, I got the same.
All right, cool. Now, that gives me the y value but I still need to find the maximum area. So I take this, and again, the y value on the diagram. This is not the y value in terms of x and y axis, okay? This is really the x location on the axis. So this is really, this here, I'll draw in white, goes in for the first coordinate of the vertex. Even though it says y, it's the first coordinate, because remember, this is a function of y. The second coordinate of the vertex comes about when I plug this into the function, okay, to give me the maximum value. So let's go ahead and do that. Let's do a of 11.68, okay, and that's going to be negative 1.07 times 11.68 squared plus 25 times 11.68. This will give us the maximum area. What do you end up getting when you plug that in?
This takes forever.
This problem took a while, yeah. This is going to take a long
Is there a
time.
problem like this on the test?
The problem on the test will take you much less time, I'll tell you for sure, but the thought process is really the same. Okay, it'll just be a simpler problem because of the time constraint of the test. Friday's test, don't forget, is only a 50-point test. It's not that long, actually. Okay, so you'll definitely finish in time. And it's an A day on Friday.
I did.
They're turning their palms at that day?
Well, if they have it done tomorrow, you can turn it in, but we can make it due Friday.
Okay, so I'll
Just come by, get it, and then you can go. Thank you, Anna.
have to grade.
Oh, you can do that too.
That's my.
Okay, what did you get?
146
No.
plus.
What'd you get, Jose? What did you get?
I didn't think.
I'm sorry, I was.
What do we get for an answer here, people?
I got 437.
I got 146.028.
146.
Yeah.
That sounds reasonable.
Let me check.
0.028.
Yeah.
The reason I said that sounds reasonable is because you're doing 25 times around 10, which is around 250. But then you're going to be subtracting whatever you get in the beginning. So it's got to be less than 250-ish. I know that already. And then 11 squared is 121. 250 minus around 120 is around 130. So this is a reasonable answer for sure. The fact that it's 11.68. Is this right, Chris?
Yeah, I got it.
Okay. Yeah, that sounds good. If you had a mistake in your calculator, it's possible that you put the parentheses in the wrong spot over here. That's the only issue I could see in this kind of a problem. Okay? But again, you could always just plug this into y1. Guys, remember, you can plug this into y1 and then go to your table and plug 11.68 into your table and it'll do the math for you. Don't forget that. You can always plug a function into y1. Now, just to check, go to y1, please. Okay? Everybody go to y1 on their calculator and type the function in. So negative 1.07. And you got to type x on the calculator, don't forget. So x squared. X is above the apps key. Don't forget, it's above the apps key. Plus 25x. Now, don't hit graph yet, please. Do not hit graph. Go to window, please. Go to window. Under x min, type in 0. Under x max, since we're only going along the x-axis up to 11.68, let's go up to 15, just to give it a little bit of room. So x max, make that 15. Make your y min, x scale could leave alone, whatever it was. Make your y min 0. And make your y max around 200, so that it's bigger than the answer we got. Okay? So we have from 0 for x min, 15 for x max, 0 for y min, 200 for y max. And then hit graph, please. You got to finish typing in the function, right? Okay, you should see part of a parabola. It looks like it's starting to come back down, but it's going to go off the screen. Does everybody see that? You should see something like this right now. Then that means you made a mistake typing in. You probably did cube by accident. It's a cubic function. Oh, when it looks like this?
No.
Yeah, those are higher order polynomials, like x cubed, x to the fourth. The number of curves is indicated by the degree.
Are the two maximums the same?
It depends. It depends on a lot more. That's something that you're gonna explore more of next year in pre-calc and in calculus.
Not excited.
This is what you should see. Take a look at the board, please, if you don't see this. This is what you should see. And remember, your y max went up to 200 from 0, and your x max went up to 15. And take a look. If you want to, what we're really trying to do is we're trying to identify this point right here, this maximum value. And if you go ahead and go to your calculator and press second, and then press trace to bring up the calculate function. Second trace. You're going to see choice 4 is the maximum. Hit number 4. So second trace, then hit number 4. You're going to get a little cursor on your screen. Go near the maximum and hit enter. Somewhere to the left of the maximum, hit enter. So maybe here, watch. Here's what you're going to do. It's going to say left bound. Hit enter when the cursor is somewhere over here. Then move the cursor all the way over here. Then hit enter over here for the right bound. And then it's going to say guess. And you can go near the maximum. And it should give you the exact value we got a minute ago. It's fine, Kate. Just hit enter there. Yep. Perfect. Kate, read your number for me at the bottom. What does that say?
X equals 11.6822, y equals 144.028.
Okay? And notice, again, the exact same values. Now, this says x and y because you're using the Cartesian axis, right? X and y. But in the problem we did a minute ago, right? This value 11.68 was actually the y dimension in the diagram. And this was really the area. Okay? Because remember, what we're plotting right now is really the y dimension and the area as a function of y. That's what we're plotting. Okay, that's what we looked at for the last example. So this is another way of checking your answer. So if you ever have a function, so let's say a simple problem I give you on the test. Ready? Find the max, or let's say min, just to make it, just a little different, of 2x squared plus 4x minus 7. Okay? Y equals, it's fine. If you wanted to do it, you can go ahead and type in this equation into y1 and just use the min function instead of the max function. But you have to think about your window. The window is going to get a little bit messy here. So if you type this in your function, in y1, and you just hit zoom 6, see what you get. Go ahead and type that into y1 and hit zoom 6 on the standard function or the standard graph and see what you end up getting. Should look something like this. Right? Something like that. It's going to be a little bit stretched out maybe on your graph, but that's what it should really look like right now. Again, you're hitting zoom 6. Hit zoom 6 to standardize the graph. Okay? And what you'll notice is the minimum value for this graph is right here at the bottom. And if you go ahead and just press second calculate now, second calculate, which is the trace key, look at the min function, which is number 3. Okay, and go ahead and do the same thing you did a minute ago. Give it a left guess, give it a right guess, and then guess on the minimum. And you should get -1, -9. Gave you an error. That means that you didn't pick the right, left, and right bound. You have to pick something that's clearly to the left of the min, then something that's clearly to the right of the min. Sorry. Yeah, that's when an error comes up, when you don't give the right, left, and right bounds. The other way of checking this, again, is negative b over 2a, which is negative 4 over 2 times 2, which is negative 1. Then you do y at x equals 1, you plug it into the function, you'll get -9. So you can check this by hand by finding the axis symmetry, then plugging it into the function, you'll get -9, or on your calculator.
It works.
Okay, it should work. Tomorrow we're going to review. Okay, make sure you finish up homework for 7-7 tonight. Okay, 7-7. The problem sets won't be due until Friday. If you haven't done tomorrow, bring them in.